Okay, welcome to the online causal inference seminar this week. We are pleased to have Erin Gabriel from University of Copenhagen speaking in the seminar this week about the derivation and usefulness of tight symbolic causal bounds for measures of benefit in observational and imperfect randomized studies with ordinal outcomes. In Q&A, today will be moderated by Emma and also Erin's collaborator, Michael Charles Sachs from University of Copenhagen. And Michael Fay from NIAID will be our discussant today. Do you want to say a few words about Q&A, Emma?
Yes, sure. So hi, everyone. We are pleased to have you back here. So as always, please ask your questions by using the Q&A button at the bottom of your screen. You can submit questions anonymously or not. As Chingyuan said, Michael will be monitoring the Q&A and answering some questions via text, and some questions will be chosen to be asked in person. So please ask your questions as soon as they come up, and we'll get to them throughout the talk. All right, I believe that is all. Erin, please feel free to share your screen.
So hi, and good morning or good afternoon, depending on where you're from. And thank you very much for this invitation. I'm very honored to be a part of this series. And as was announced, I will be talking about the derivation and usefulness of tight symbolic causal bounds, and I'll talk about what that actually means. And in particular, I'll give some examples in the measures of benefit in observational and imperfect randomized studies for ordinal outcomes. Sorry. And this is joint work with Michael Sachs, who's going to moderate the questions, Arvid Hulender from Karolinska Institutet, sorry, and Andreas Jensen and Gustav Johnson from Karolinska, and Andreas is from Copenhagen University with Mike and I. So just to give a little bit of background, I think that probably everyone here in the causal inference, looking at the online causal inference meeting, is aware that causal estimands can be non-identifiable, and deciding whether or not those estimands are identifiable is sort of a closed problem, although I'm not saying it's easy to do in all cases. There is a recipe for doing that, and the algorithm is complete. So I'll call it Pearl's recipe. You commit to a DAG, a causal graph. You specify an estimand of interest, which throughout the talk I will occasionally call a causal query. And then you can determine if that's identifiable. So if it is identifiable, it will return the estimand in terms of causal, in terms of observable probabilities, and then that will suggest an estimator. And so I would say that this is the place where a lot of modern causal inference is working, right? We make the necessary assumptions to make the estimands of interest identifiable in our DAG or in our universe, in what we're willing to estimate. But what do you do when an estimate is not identified? So you could, as I said, make more assumptions, but let's say that you don't want to do that. Then one solution, or the solution I'm going to suggest, is to bound the range of the values. So I've been saying bounds a lot, but let me define it. So bounds, it's just a range of the possible values of the estimand of interest that allow for the lack of identifiability. So although some people use bounds when they're discussing the bias or the selection bias or other types of bias, and they might be bounding that bias, I will always be referring to a bound that bounds the range for the estimand, the causal estimand of interest. And other terms that I've used in the title, and I will use throughout the talk, is non-parametric, and by that I just mean without parametric assumptions, so no linear structural equations, no distributional assumptions. I'm just going to assume a DAG and assume that DAG encodes non-parametric structural equations. The term valid, and this just means that the bounds, when connected to bounds, means that they include all possible values of the estimand. Tight or sharp, which I use and I believe are used interchangeably in the literature, just means the bounds don't include values that the estimate cannot take on. So given the current assumptions, they don't include anything that the bounds can't have, okay? Or the estimand values the estimand can't have. Symbolic, these are just expressions in terms of the observable true probabilities, and they're not numbers. They're just in terms of the true probabilities. And that means that it doesn't involve data, it just involves the assumed DAG. And then numeric, and this is versus symbolic, it's only within a given set of data. And it also assumes the DAG, or the relationship between the measured variables and the unmeasured variables. And you can either obtain these numeric bounds by plugging into symbolic expressions or by directly optimizing the data that you have under the assumed DAG to get these bounds. Okay. So today I'm going to specifically talk about 3 variations on the probability of benefit. And so psi, theta, and phi here, these are just the probability of no harm, the probability of benefit, assuming without loss of generality that larger levels of y, the outcome is better, and the relative effectiveness. So the probability of benefit minus the probability of harm. So here, y is our outcome. It's ordinal, having several levels that are ordered, and yi is the counterfactual. yi1 is the counterfactual outcome under x equals 1, versus yi0, which is the counterfactual outcome for an individual I under control. So as you can see in all of these expressions, they involve the joint probability of the counterfactual, the joint distribution of the counterfactuals, which without very strong assumptions, we know nothing about. These in even perfectly randomized cases where y has more than 3 levels are not identifiable without very strong assumptions. So going back to bounding in general, the first, or I believe to be the first set of bounds that are using the linear programming method that I will discuss was Balke and Pearl in 1994 in Balke's thesis. They bounded the now famous IV setting where Z, X, and Y are measured binary variables, and U is an arbitrary, potentially set of unmeasured confounders between the exposure of interest and the outcome. So you measure these variables, but all you assume is that they have this DAG, and thus they have these encoded non-parametric structural equations. And then we're interested in, and sorry, I'm using theta again here, this risk difference between the probability that y under treatment and the probability of y under control, the difference between those. And this is not identified in this IV setting without additional parametric assumptions at the population level. So Balke and Pearl derived bounds for theta with no additional assumptions using linear programming. So what does that really mean? So to go from a DAG to a linear programming problem that you can solve to get these bounds, you need to connect the observable probabilities, which we denote here as P, to the unobservable and unestimable response functional counterfactual probabilities. And so those can be written, there's a set of the response functional counterfactuals, which are just the pathways from parents to children that determine fully, how those children take on their values. And all of the observables P have some set of them that they're equal to. If this is linear, then the constraint space implied by the DAG is linear. Further, we can express the potential outcomes of Y just using the adjustment formula based on these counterfactuals. Additionally, and because of this, we can then put that theta, that risk difference, in terms of the Qs, those response function counterfactuals as well. And so then we have these constraints as well as the estimand of interest that we want to target, all in terms of the Qs. So then we also know some other things about the Qs, given that they are probabilities and that they're joint probabilities. They sum to 1 and they all have to be greater than or equal to 0. So if we could observe the Qs, this would just be, a standard linear program we could solve. But unfortunately, we can't solve this symbolically and have it be useful because we can't ever estimate the Qs. So instead, we want to convert to the dual of the problem through these constraints to be in terms of the P's, the observables, and then do the optimization. And we know that this will also be optimizing the thing we're actually interested in, or minimizing the thing we're actually interested in, the estimand, because of the strong duality theorem, which means that we can solve this problem in terms of P's and still know that we're actually minimizing or maximizing in terms of the Q's. Further, because it is a linear problem, we know that the constraint space is a convex polytope, and therefore the maxima that we're looking for, the minima that we're looking for, are always the vertices of that polytope. So then we can just enumerate them, and this is the classic vertex enumeration. And in our case, in our package that does this, we use the double description method that's implemented in the cddlib package, which is quite fast and well tested. So although it might just seem like a straightforward use of linear programming, it's really the conversion from the the non-parametric structural equations, or the DAG, to these constraints that was originally the bottleneck for people using this method. So in a recent paper, my group has developed an algorithm going from a DAG and then non-parametric structural equations to these constraints implied by the DAG. Well, we also have an algorithm for converting a estimand or a target into the Q space as well. And although, these are written out as though they're linear, it's not always clear what will be linear just directly looking at the DAG. And so we prove that there's a class of DAGs and estimands for which it will always be a linear programming problem. So if you use our package Causal Optum, it will restrict you to this class of DAGs and estimands, and it won't attempt to do the bounds outside of that. That's not to say that there aren't linear cases outside of this class of DAGs and estimands of interest. It's just that we know that these are and will always be linear. Okay, so this is an example of a slight extension of the Balkian Pearl setting, where we now have two IVs on what we would call the parent side of the DAG, and then we have the same unmeasured confounding between the exposure and outcome. So this is an example of something that we have and are now able to bound quite easily because of the package and the algorithms. So the computational advancements that we've made are these algorithms work for a general class of causal problems, including multi-categorical variables are allowed. Additionally, we can do many things more than the risk difference. We have a recent paper bounding the natural direct effects and like many of the decompositions of two ordered mediators. We've implemented an interface in the R package, which is a shiny interface, so you can draw the DAG that you're interested in like you would in DAGity. And then, as I said, we have sped up the vertex enumeration. And because of that, when you're directly using a case where linear programming applies, we're able to derive bounds in new settings very quickly. And this allows us to do it in many, many cases and detect patterns. And you'll see that later, we were able to use that in the ordinal case. And then we're able to derive general conditions. So to put this in perspective, the first papers about bounds using this linear programming setting had 1 to 3 sets of bounds, generally for the same DAG, under slightly different sets of assumptions. And on average, over the last 35 years, it's been a similar pattern, 1 or 2 bounds per paper. So in a recent paper, we derived 35 sets of bounds in a setting with 2 ordered mediators, and these were all of the decompositions for the two ordered mediator setting. And this led us to some more understanding about the use of bounds. For instance, the addition and subtraction of type bounds does not universally result in type bounds, although it does in some cases. So even though 2 pieces or 3 pieces in a decomposition will add to something, adding or subtracting their type bounds does not result in type bounds for that remaining piece that they're decomposing. Okay, so I've talked about how we're able to derive these tight non-parametric bounds using linear programming, or our method for doing it. But how are these symbolic bounds specifically, rather than numeric bounds, useful? So they're useful particularly to describe and look at information loss in the case of study designs in the absence of data. For example, in a recent paper, we looked at outcome-dependent sampling settings, and some of those lacked randomization and some of those included an IV. And in that example, we found that it really was the lack of the IV that caused you to not be able to, or to have very wide bounds that almost always included the causal null, whereas the outcome-dependent sampling could be mitigated by that IV or that randomization at the beginning. So similarly, you could use these symbolic bounds under a given design to compare different estimands of interest. For instance, you would know that the probability of benefit is probably not going to be identifiable, but how much less identifiable is it than some other estimand that you're interested in under the same DAG or the same design setting? Or under different DAGs, for the same estimand, like we did in the outcome-dependent sampling, you can compare the information loss. So for example, you might think when designing, let's say, a randomized trial, that perfect compliance is not possible. And so you decide not to randomize, but this would to me be an obviously poor choice because that's what's going to drive your ability to exclude the causal null in many cases. And you're going to have more identifiability, you're going to have narrower bounds with the IV in general than without it. Okay. It's often said that these bounds, particularly non-parametric bounds, are too wide to be useful in applied work. But a counterexample to that is an example we've used in a number of papers is a randomized trial that had both non-compliance and dropout, and it's a peanut allergy study. And it was originally published in 2015. And it enrolled infants and instructed their parents to give them a certain number of grams of peanut snack a few times per week, or to completely avoid peanuts. So, and the outcome was allergic reaction during a controlled oral food challenge at the end of the study. Compliance was assessed both with the questionnaire and by actually looking for peanut powder around the house. And their results, the original results, found a positive effect of peanut exposure on reducing allergic reaction, but they didn't really attempt to account for non-compliance or dropout other than doing the worst case scenario imputation. And so we reanalyzed these data using bounds that accounted for the non-compliance, and we went for the actual treatment effect rather than the ITT. And we see there's a strong effect. We exclude the causal null, and we see that there's a strong effect of reducing risk of reaction when you have been exposed to peanuts. So I think in this case, it sort of is a counterexample to the fact that the non-parametric bounds will always include the causal null, will always just be too wide to be useful. And in this case, I think it's a much stronger support of the peanut exposure than the simple worst case scenario imputation of the ITT. Okay, so now I'm gonna move back to those measures of benefit. So some specific examples of where bounds are useful, because they're never identifiable, even in perfectly randomized trials without very strong assumptions that you know something about the joint of the counterfactuals. So again, because they aren't identifiable even in perfectly randomized trials, there are a number of papers that give both symbolic and numeric bounds that are valid, all of them, but some of them are tight in the perfect randomized trial setting. So that would be this DAG, the A DAG, the perfectly randomized trial with no confounding. But to our knowledge, no one has ever looked at bounds for any of these estimands in the completely confounded settings, the observational setting, where there's a possibility that there are unmeasured confounders between the exposure and the outcome completely, and there's no IV. There's also a few works in a non-compliant setting or an IV setting. However, most of them make assumptions about monotonicity, and they target not the population estimands of these benefit measures, but a different measure that would have marginals that are identifiable. So most of the bounds are through the marginal counterfactual probabilities, which in some of these cases, or in all of them, those won't be identified. Okay, so because we were able to use our bounding program very quickly, we were able to do these bounds under DAG B in the confounded setting for a large number of levels of Y, so discrete ordinal Y up to 9 levels. And because of that, it was very easy to see the pattern of the bounds over those numbers of setting, and this led us to be able to determine this pattern and then prove that in general, for an arbitrary number of levels K for the ordinal outcome Y and a binary exposure, that these bounds generally are both tight and valid. So theta here is the probability of benefit, sorry for the difference in order, and psi is the probability of no harm. So that's just this with the including inequality. And then the phi is the relative effectiveness. So that is a difference in probabilities, and thus has a natural or complete range that is -1 to 1. And so you can see that we are able to potentially make that tighter than -1 to 1. Similarly, in the case of the no harm, probability of no harm, the upper bound is 1 in all cases, but we're able to potentially move up from 0. And then in the probability of benefit, the bounds will always include 0, but we are able to potentially move down from 1 to say something more specific about it. And this is just to say that these probabilities are the joint probabilities between x equaling I, so 1 in this case, and y equaling the given level j. So in this case, it's the probability that you have x equal to 1, so the treatment, and y equal to the lowest level 0. So in this case, the probability of benefit, I think this bound makes sense. We can only bound it above 0, but we are able to exclude these probabilities from 1 that would be clear indications of harm. So under the treatment, harm or equality with between the control and the treatment. So this joint probability is that you were under treatment, but you had the lowest value of y. So that the only possibility there is that the treatment is causing harm, or that the treatment is equal to the control. And in this case, again, this is under control for x, and then the highest level of y. So if we're assuming without loss of generality that higher levels of y are better, then this means that the control is achieving the highest level of y, and that can only be equality, or that the treatment is causing a lower level of y. So I think this one intuitively makes sense in generality, where the others do as well, but I won't discuss them in as great a detail. So under DAG C, which is the IV setting, just with an ordinal y, we were not able to find a general pattern, and we've calculated the bounds up to 7 levels, and we've included in our archive paper on this topic R functions that give the expressions up to 7 levels. without assuming notifiers and also with assuming notifiers under this IV setting. But they are generally, some of them have 100 terms in the expression, and I don't think they're very intuitive to express. They're useful to use to actually have the bounds, but we were unable to detect so far a pattern in them that would lead us to a general bound for an arbitrary level of y. So I think more interestingly, we might look at the simulations. I think that's a more interesting look at these bounds in the cases of non-compliance, where often they have too many terms to really take in. And so we've looked at these in a set of simulations where the probabilities for k, the ordinal, the probabilities over the number of levels of y, k, are somewhat uniform. Okay, they're not restricted to be always uniform, but they are tending towards uniform. So although we see general patterns in the simulations, that's not to say that this is always the case. But in our simulations, we find in the confounded setting, that's the DAG B, the one where there is an unmeasured confounder between the exposure and the outcome. We see that as the levels of y go up, we tend to have wider bounds. Okay, and that's for the probability of benefit, the probability of no harm, and that relative effectiveness, the difference between the probability of benefit and the probability of harm. In all of these cases, we have a tendency to move up in the wideness of the bounds. And again, that's likely because the probability laws that we're generating tend towards the uniform. So in these bound expressions, these are joints, and these are tending to get smaller and smaller with more and more levels of y, which makes sense. So in the non-compliance setting where we're making no assumptions about monotonicity or notifiers, we see a similar pattern. And in all cases, these are different measures, of course. The natural bound of the difference between probabilities is up at 2 for the width. And these are, of course, the widest bound they can have is 1. So that's the difference between the measures in all cases. But we can see as we move from 3 levels to 4 levels to 5 levels, that we start to see a stretching out. And this is approaching, it's going over 1.5 in the width. So these are all the width of the bounds. So in the non-compliant setting, assuming monotonicity, we see an interesting pattern that they're very similar bounds between the non-compliance not assuming monotonicity. This is a similar thing as in the standard IV setting for the average treatment effect, where the bounds assuming monotonicity are actually implied by the bounds not assuming monotonicity when you actually have monotonicity. So we haven't proved that to be the case, but it seems to follow here as it does for the average treatment effect. These are the bounds that were previously derived in lieu, and for several other people, several other works also derive these in the completely randomized or perfectly randomized trial setting. And as you can see, they have a similar property that as the levels of y increase, the bounds become wider. Also, you can see that in the randomized trial case, there's a much larger group that is identified. So although they're not identified non-parametrically, given the bounds, the upper and the lower bounds converge. And so in any case where you see there's a point around 0, that means that the upper and the lower bounds have converged. So back to that peanut example that we've used in a number of papers. So here we've used our outcome, y is 3 levels, which is the amount of peanut powder you tolerated during the end oral food challenge. So it's either 0 to 4, meaning you had an immediate reaction, or a small amount of peanut powder caused you a reaction. This is like a moderate amount. And then above 8 grams, you basically didn't have a reaction, or it took a large amount of peanut butter for you to have one. So these have slightly different names, but the assignment effect, that's the perfectly randomized trial, except for we use the randomization. So you can think of this as a perfectly randomized trial, but for the ITT effect. And then the treatment effect, ignoring assignment, that would be the observational setting, the completely observational setting. The treatment effect, this is the treatment effect in the IV setting, so the non-compliant setting, but not assuming no defiers. And then this is the same effect, assuming no defiers. So as you can see, in all cases, the widest bounds are in the treatment effect, ignoring the IV or ignoring assignment. And in these two cases, you can see that it includes what I would call the causal null. So specifically in this case, where there is a clear causal null of 0, it will always be included in these observational bounds. However, you can see that the probability of no harm in all cases had an upper bound of 1, and that in general, they agree across all possible boundings, except for in the observational case where they're much wider. Similarly, in the probability of benefit, we see very similar levels over the assignment effect, the treatment effect, and the treatment effect assuming no defiers. This could be because there wasn't a large amount of non-compliance. And you can see that, again, the largest bounds, and these being really large, are in the observational setting. So then there, again, the pattern is that there's not very much difference over them for the different settings, except for in the observational setting when you really cannot exclude the causal null. Okay, so thank you very much. And I'm happy to take a few questions, I think, quickly for clarification before we move on to a discussion with Mike Fay.
Thank you, Erin. So yes, I would encourage everyone to submit questions through the Q&A. Do you have some? Actually, Chingyuan has a question and I do as well. So I think mine is short. So let me ask it first and then I'll give a chance to Chingyuan to ask. Could you go back to slide 17, please?
Yes.
Right. So in the middle example, the one that you have with confounding, are you assuming that you always in this DAG have a causal effect? Because to my understanding, like one reason that maybe there's not a lot of bounds in the literature for this case is that we cannot really distinguish between this graph in the middle of B and the one when there is no causal effect of X on Y.
Right. So we are not assuming that there is a causal effect. We're simply allowing for it. And in all cases, our bounds under this fully confounded setting will include the causal null where there isn't a causal effect. There's no way to exclude that here.
Would that mean that, sorry, just a short follow-up, would that mean that it's always including 0 in this case? Or did you notice
so it's
any
always
cases
including,
where
it's always, so I shouldn't say the causal null. It's always including 0 in like here where there's a difference. Yes.
Mm-hmm. Okay. Great. Thank you so much. Chingyuan, please. Thank you for the answer.
Oh, there's a question, short question from Q&A by Robin Evans. Maybe we should just do that here.
Yes.
Do you account for uncertainty in the bounds?
So that's a very good question, Robin. So everything that I've talked about so far has been the true probabilities, which of course we don't observe, the true observable probabilities, which we don't observe. You have to estimate them. And so in previous works, we've talked about using Bootstrap for, expressions like this. There are some problems with using the Bootstrap, and we are working actually with Mike Fay. Michael Sachs and I are working with Mike Fay on potentially using exact expressions to account for uncertainty or sampling variability when estimating the numeric version of the bounds. I hope that is what you were asking, Robin.
Okay. Yeah, he says, thanks. I have a my own question is about how these symbolic bounds are derived. Sorry if I missed that. I think you mentioned the linear programs. Do you basically solve these linear programs analytically using some kind of symbolic computing software?
Yes, we use it. We solve it analytically with, sorry, I'm a little lost, with vertex enumeration.
Okay, so, but why is it useful to get a symbolic expression of these bounds instead of just doing some numerical optimization every time when you have a data set?
Well, for one, it can be very time consuming to do the numeric optimization for each data set. Specifically, if you know what the trial design is, and so it would be the same each time symbolically, and the only thing that would change is the estimates of the probabilities that you would plug in. But secondly, sorry, going to this, symbolic bounds can give you information about the information loss due to the design of the study, rather than due to the numbers that you're getting out of the study.
Okay, but later on, you also mentioned that sometimes you have 100 terms and it's very difficult to interpret these bounds. So how do you exactly see this information loss?
Okay, so you can simulate probability loss for the joints.
I see. Okay, I see. Okay, and you don't need to numerically solve every time, and you can just plug in the expression. Okay, that makes sense.
Yes.
I have another short question, unrelated question about the outcome. So you've done this for ordinal outcome. What about if I have a continuous outcome? Do I simply discretize them and apply this method, or what would you recommend me to do?
So you can do that. There are some of the bounds that have been derived are for in a similar setting for these. Sorry, I'm trying to get to that. So for these, some of these papers, Fei and Lu, include a continuous outcome Y. So they have bounds in that setting, but only for the perfectly randomized setting. So if you're in a different setting, I don't believe there are bounds that have been derived for those. So currently, yes, discretizing is maybe your only answer. I don't believe there's like a one-to-one, like, oh, if you take it to the extreme, these bounds apply directly in the continuous case. I think there is a need to derive new bounds in the continuous Y case. But I'm unaware that that has been done, but possibly I've missed it in the literature.
Yeah, thank you.
Yes, we don't have any more open questions now, so maybe we move on to the discussion, and so we'll have some time at the end. So Michael, please feel free to start sharing your screen.
Okay, thanks for inviting me to discuss this nice talk. Let me see. Oh. So I guess, you know, what's really nice about this work is, you know, they took the idea of Balke and Pearl of linear programming, and then they kind of dove deep into all the stuff that's been developed in linear programming and the strong duality theorem and all the stuff that I don't know anything about. And they use this stuff that is really useful for causal inferences. Sometimes I think that's when the best research happens, is when you pull stuff from another area that's all well developed, and you can apply it to a new area like causal inference, and you get all these great results. So the paper by Mike Sachs is the first author, kind of describes all this stuff and clarifies when you can use this linear programming. And I you know, none of these papers did I thought if I discuss this, I'll really learn this stuff, but it's going to take a lot longer than this. But it's really nice papers. And the other one is binary treatment outcomes with confounded missingness. And the last one has two binary mediators. And I even left one out that you mentioned about the outcome dependent sampling. But most of these are like the simple cases of where the difference in means is the causal estimand, and they have binary outcomes. And I just wanted to go quickly a little bit more into the New England Journal paper, peanut allergy, the paper. So you know, in clinical trials, they predefined the primary endpoint, and so it was a binary endpoint of whether you had an allergy or not. And you can see that it has these huge effects where avoidance is where you get randomized to you don't have your kids, you have your kids avoid peanuts, and your infant kids, and then consumption is when you feed them. And you can see that, you know, in the intent to treat analysis, you have a huge difference, 14% difference in the rate of peanut allergies. And then the protocol in the New England paper, they just did a naive thing, which causal inference people would never do, but they just said, well, if you follow the protocol, then let's just only use those people. And then it looks like a really big effect, but we all know that's not quite the right way to do it. And the nice thing they did in the paper was a worst case imputation, but as Erin said, it's really estimating the intention to treat effect, but it's still there. And so with Erin's paper and this work, it's really a way to rigorize the inferences. You might say, oh, there's a huge effect no matter what happens, so why make a big deal? But you know, science is about making things rigorous. And look, if you look at the last thing that Erin has, the treatment difference effect, they did it the right way. You know, they didn't do a naive per protocol effect. They looked at the treatment effect and got these nice lower and upper bounds. And in the paper, they do the bootstrap compositables on those upper and lower bounds. And this allows for the confoundingness of the missingness that can depend on the treatment and the randomization and the unmeasured confounders. So for the ordinal, so Erin, I think I obviously didn't understand everything in your papers, but I think I missed the part that you're using linear programming in the ordinal work also. I don't know why I missed it. I think because you saw the pattern, then you proved the thing without using the linear programming, and then I got mixed up. But so this has a wide use, and especially with the ordinal. I'm just going to focus on this probability of no harm and the two simple perfect randomized trial and the confounding example. So I like to start with simple DAGs because I'm not really a causal guy. So the you know, in a randomized trial, you can calculate a causal effect, which is a population relative causal effect, which is the Mann-Whitney parameter. And it's not really causal to a lot of causalists, because you're not estimating the effect of the treatment on each person or an average effect of each person. You're comparing the population of people who got the treatment and the population of people who got the control. And so it's not you look in that probability statement of no, I use a separate index of J and I to indicate that you're not comparing the same person to themselves of their counterfactuals. And what's nicer for interpretation causally is to have an average treatment benefit on individuals, but unfortunately, it's really, you can't get it in a randomized trial, even with a randomized trial. And I think Erin mentioned that there were other people who did bounds for continuous data, so I just thought I'd give this. Here's if your marginals are continuous, your proportional, your potential outcomes are continuous, you have this nice bound. This basically is saying you take the maximum difference in the cumulative incidence, cumulative distribution functions, and that's your bound, your lower bound, and then the upper bound is some function of that also. So it's a really nice bound. And then when you have discrete outcomes, you can kind of write it like that also. And this is work Erin didn't emphasize this because this is previously done before her work, but you can get these nice bounds in the discrete case also. So here's the case with the unmeasured confounding. I like to put my causes before my effects and swing it away over there, because I'm a English reader. and I like causes to come before effects. But anyway, so here's the bound for the probability of no harm, and I'll just rewriting it in terms of probability. So it's the probability that you get the control and you have the lowest value of the response, plus the probability that you get the treatment and you get the highest value of the response, and that's your lower bound. I know, Erin, you talked about, in answering the questions, how as you get more and more categories, I thought, well, if it's uniform, then for sure it's going to be a problem, because you're going to get essentially lower and lower values in the bound, and essentially your bound is going to approach zero. So it seems like with nearly continuous data, if we have unmeasured confounders, not only will we always include the null effect, but we're going to have no information essentially, without extra assumptions. So just to start some questions, I had some questions. For the confounding example, I think I just kind of asked this. With the lower bound approaches zero as the number of categories goes to infinity, if you have a uniform case, then, so can we say with continuous data, if there's a confounding, then you don't have to stop looking for a bound, because it's just going to be zero anyway. I mean, you can, if you're a math person, you can spend years looking for it, but I don't think it's going to be there. Don't answer it yet.
Okay.
You can answer that. Go ahead, answer that first one.
So, okay, I think you answered your own question. Like, if it is uniform, yes, it's going to approach zero, but that is a statement about the amount of information that you actually have in your potentially confounded observational setting. So I think it is useful to know how little information you have. I don't think there's a one-to-one correspondence between the discrete bounds and the continuous bounds. I think those would be based on.
What do you mean by that, a one-to-one correspondence?
I think that though the continuous bounds need to be based on the CDF, and so like just saying these approach zero, there's probably there is a difference between the discrete bounds and the continuous bounds. And so I'm unwilling to make any commitments about the continuous bounds that I haven't really thought about. But in the cases where it's not uniform, where you have a very lopsided distribution, where you aren't choosing the categories yourself, so you're restricting them to be more uniform, or where you prescribe them before looking at the data in, let's say, a trial, you could get much larger probabilities at the top or the bottom. So these bounds could be very useful. I don't think it's necessarily the case that just because you get more and more categories, you're going to get less and less information. We saw that in our simulations because we were generating things that were uniform.
Okay. My other question is basically, can you talk more about, this linear program and the strong duality theorem and all this other stuff? It seems like you have a whole tool of stuff that can be applied to a lot of problems, but then I got mixed up about, how big the class of problems you could apply it to. Maybe you could talk a little bit about that.
Okay, so basically there's many more estimands than just the mean difference of the average treatment effect that you could apply these to, and we've looked at the natural direct effects, the natural indirect effects, and the controlled direct effects, and now these ordinal outcomes, as well as the average treatment effect over a large number of DAGs. I originally thought your question was, does this apply outside of bounding? And potentially, I haven't thought about it, but possibly, I think there is a correspondence because we're always, but maybe I can only think of a use of it in bounding problems. But it definitely applies to a much wider range of problems than we've applied it. Many more estimands, and in many different settings. So as you can see, like just from the ordinal case in the non-compliance, as the categories, the levels of Y go up, we get lots of terms in some of the cases. And so each of those had never been looked at before. So I think there's a lot of different cases that are still open for this to be used on.
One thing as a vaccine person, when we measure mediation effects, we don't use differences, we use ratios. Is that throw everything out the window with that stuff?
So currently with our method, yes, but we are looking for ways to have things that are the transformations of estimands that are technically nonlinear into linear estimands, and then working back and still preserving the tightness of the bounds. So that is something we're currently working on, but right at the moment, no, we can't give you tight bounds for things that are ratios. We can give you valid bounds by just taking the ratios of the two sets of bounds.
Thanks. That's it for me.
Okay, I'm happy to take any other questions.
I have another possibly stupid question. Are these all problems like this? Will they all reduce to a linear program? And if so, why?
Sorry, I didn't quite understand that.
I guess it seems that the methodology relies a lot on writing these bounds as the solution to a linear program.
Yeah, it completely relies on that, our current method.
Just want to ask how general that strategy is.
It's pretty general. It applies to an entire class of DAGs where each measured variable can have an arbitrary number of levels. And where the DAGs just need to be divided. I could share my screen again, maybe.
Why is this has to be linear?
So it doesn't necessarily have to be linear in general but to use the methods that we've made algorithms for, it needs to be linear. So to use, for instance, our causal optim R package, they need to be linear. There are solutions to nonlinear problems. We just haven't found a general one that applies to a full class of nonlinear problems. Symbolically, of course, there are numeric solutions to nonlinear problems.
Okay, because I imagine you need to somehow parameterize these conditional independences constraints.
Yes,
in the problem,
and so that's why it basically comes down to DAGs that look like this or something similar, but they can also be for other estimands. So you'll have a parent side of the DAG, which will contain an arbitrary number of IVs with arbitrary number of levels, and then it's blocked by an exposure. But we've also extended this to settings that would be considered not necessarily perfectly linear when we have outcome-dependent sampling or sampling in general. So we can deal with that nonlinearity already, but extensions to things like where the estimand is a ratio or where you have nonlinear constraints implied by the DAG, we only have solutions that provide valid but not tight bounds currently.
Thank you.
You're welcome.
There's a question in the Q&A now. When would you recommend your bounding approach over doing quantitative bias analysis? Okay,
so maybe I'm not 100% sure what you mean by quantitative bias analysis, but if by that you mean some sort of sensitivity analysis where you say something about the distribution of the unmeasured confounder, or can you unmute them and they can just tell me what they mean?
Yes, that's what they were referring to. Yeah.
Oh, they said yes. Sorry, I thought you said yes, I will unmute them. Very sorry. So when you have information about the things that you think are unmeasured, you should obviously go with the quantitative bias analysis because the non-parametric causal bounds will make no assumptions. So they will be much wider than you're willing to use, given that you know something about the things that are unmeasured. So if you have information about the things that you think are unmeasured, you should go quantitative bias analysis. And if you have no idea about what you think could be unmeasured, or if you want to allow for just an arbitrary set of unmeasured confounders with any distribution, bounds, either numeric or symbolic.
Okay, we don't have any more questions for now, so I'd like to thank Erin for the really nice talk, and Michael for the very insightful discussion, and it was very interesting to learn this line of work. And thank you for keeping very good track of time. So this is a perfect point to announce that there will be no online causal inference seminar next week. We'll be on a summer break, and I hope I'll see you after the summer.
Thank you very much.
Thank you.
Thank you.